Hello, I'm Justin Hominski, or Professor J-Dog, and today I'm going to be going over problem 22 from chapter 10 of our textbook, specifically sinusoidal steady state analysis. So that consists of phasors and phasor analysis using the same methods as chapter 4 or, nodal analysis, anything like that. Yeah. So the problem I was given was question 22, or actually the problem that I picked was this one here. So the reason I picked this one is because it was simple, but yet effective at explaining all the steps when it comes to phasor analysis and how to solve a problem that it looks like this. So no matter how complex it is. So essentially you want to start off by just looking at the question and reading it and understanding what's going on. So here what we're given is that there's a source, it's a current source specifically, and it's 2 with an amplitude of 2 cosine 5t amps. So what that means is that 2 is our peak, is our amplitude, and cosine 5t. 5t is our omega, which is our angular frequency. And since it's in cosine, we can take that as 2 angle 0. If it was in sine, we'd have to subtract by 90. But since it's in cosine, it's given to us that our I source is going to be 2 amps. There is going to be no imaginary unit. It's just purely 2 amps real current. And in this case, we have an inductor and a resistor that are both in parallel, all sharing the same node. And IL is labeled as the current down the inductor. So first things what we want to do is we want to convert everything to phasor form. And like I said, the IS is just going to be 2 amps. And that is actually not in phasor form. It'll be 2 amps angle 0 would be kind of the phasor form. But it's easier to look at it this way because then it kind of doesn't make it look as complex. And then our inductor, which is 0.4 henries, we're going to convert that into its impedance value, which is the phasor form. This is, when I say phasor form, this is Cartesian. So where we use reals and imaginary. And so this is actually like the Cartesian form, the way I wrote it, but you can convert it into phasor form or however you'd like. But essentially the impedance value for a inductor is going to be J omega L, where J is the imaginary and omega is the angular frequency. And then L is the inductance, which is 0.4 Henry. And now, what is this device? So this device is essentially a coil that's wrapped around a piece of metal. And what it's essentially doing is it's storing a magnetic field. And when there is a current applied to it, it stores that energy and releases it and dissipates it as time progresses. So after we've done that, we're going to use current division to find the current down the inductive branch. So if you see, they all share the same node. So we have 2 amps flowing in, and then we have some flowing out into the inductor, and then some flowing out into the resistor. So we can do current division and do IL, which is the current down the inductor, is equal to 2 times the ratio between the two. So 2J divided by 2 plus 2J, which will give you 1 plus J amps. And then that's, if you take the square root of both, so 1 plus 1 squared plus 1 squared is equal to square root of 2, angle of 45 degrees. So 45 degrees come from the tangent of both of them. So if you do the tangent of y over x, which is the imaginary over the real, which is going to give you 45 degrees because the tangent of 1, right? It's 1 over 1. Anyways, yeah, so then when we convert it back into the time domain, IL of t is going to be square root of 2, which is going to be that amplitude that we got. Cosine, we're dealing with cosines, not sines. And then parentheses 5t, which is our original omega, plus 45 degrees. How can we verify this? So you can choose you can choose any method essentially. But for this one, it's easy to look at it and go, well, let's just do mesh, right? You could do power absorbed and calculate it and make it equal to 0, but let's do 2 meshes. So we have one loop on the left, I1, one loop on the right, I2, and we know that IL is the middle branch in between, which is the current down that inductor, is going to be I1 minus I2. Okay, and if you take a glance at this, we know that I1 is equal to 2 amps, okay? And then 2J, so if you look at the right loop, I2, we're now having to relate that equation, and if you multiply 2J, the inductor, by I2, which is the opposing current, which is actually the current going into it, and then the opposing current, I2 minus I1, plus 2 times I2, which is the resistor. If we simplify that, we get that I2 is equal to 1 plus I. I1 minus I2 is 2 minus 1 plus I, which is equal to IL. And we verified that, and that's exactly equal to our nodal analysis, which is square root of 2 cosine 5t plus 45 degrees. Here's some conclusions and key takeaways. Essentially what we did, solve nodal and mesh. Both methods confirmed our answer, reinforced our concepts of impedance, division, phasors, just basic concepts, and confidence in RLC steady state analysis, which is preferably easier than writing out derivatives and zero input, zero state. So thank you so much for watching. And of course, I'm Justin Ominski. If you have any questions, feel free to let me know. Have a great rest of your day.